Okay, we have finished the book by Oliver Morton called The Planet Remade. I'm going to add a few podcasts from this book by Ronald Hester and Roy Harrison called Geoengineering of the Climate System. This is much more of a direct science book, unlike Oliver Morton, who wrote it from I guess, a journalist's perspective with science. I will add points that I think are additional in terms of the points that we haven't covered in the other book. So starting with, again, briefly why we need geoengineering and carbon storage, solar radiation management, etc. This is a good figure, another way to look at where we have been and where we are headed. So this is putting the carbon dioxide in the atmosphere from from David Keeling's, Charles Keeling's data, but has taken out the annual cycle and just showing the trend, and puts lines of where we were at certain times in the 1970s. If we stuck to it, would have been at 380 ppm by 2030. We would be, and there was another option to go stay at under 410 and so on, but here is where we are headed by 330 to be almost 450 ppm or higher. This is what we would call as business as usual, and you can see various timelines of the Rio summit from the early 1990s, COP 1, 2 and so on, COP 15, the Copenhagen Accord, Kyoto Protocol came and went, of course. Paris Agreement is now underway, and we have had several COPs after that, including COP 25 in Chile, Madrid. Because of COVID, it got moved and so on. So essentially the point is the questions we asked before from Ron Sokolov of Princeton: do you think climate change is something that needs action, and do you think it's easy to accomplish it? So the idea is that geoengineering should still stay on the table as an option. Okay, if you don't believe it, then you have to answer those questions to yourself. The first chapter is on this idea of why we need geoengineering. I'm going to skip it because we covered it in a couple of podcasts in the other book. The second one here is on storing carbon for geologically long timescales to engineer climate. Some points here were not made explicitly in the other book, so this is a good diagram, for example, showing the size of the challenge for engineered carbon production and storage. Here we are at fossil fuel emission business as usual by 2050 would be at 60 gigaton CO2 per year, and we are here at 2010 at about 30 gigaton, and now we are almost at 40 some gigatons by 2021. COVID came, reduced emissions, and now we are headed back up. Energy efficiency would give us so these are gigaton CO2 on this axis, and here are what we could draw out. So for energy efficiency would give us drawdowns in this range. Fuel switching, so renewables, geothermals included, and just switching the system from carbon dependent to renewables, and renewables themselves. So that would give us minus 40 gigatons over there. Carbon capture and sequestration is in this range. We will see another table of this. Switching to nuclear would reduce carbon emissions by some around 15 to 20 gigatons. And on this axis we have cost or ease of application in terms of dollars per ton of CO2. So you can see that these are still reasonable, but we still have to kind of find the finance for it, in addition to the political will and the regulations and so on and so forth. So this is the carbon dioxide removal methods with various costs. None of them is very cheap right now, and possible co-benefits in terms of increased agricultural production is expected to make them more attractive, but so far no real movement on that. So you have many technologies that are not necessarily scalable, but even at the scales at which they operate, the expense of or the cost of application is quite high. Okay, so that's kind of the challenge we are facing. We talked about in other ways, but here we are in terms of costs. So here in costs, dollar per ton of CO2 abated, another way to look at it, and the tonnage stored in terms of gigaton CO2 per year. Direct air capture is up here, so high costs, but has a range of tonnage stored possibilities here. We talked about enhancing ocean alkalinity, expensive, but also not large in terms of storage of CO2. BECCS, bioenergy and carbon capture and sequestration. We talked about a lot of issues of finding land. Remember that if you look in my course drawdown, we talked about the area needed. I also showed it in one of the slides, one of the podcasts here. The area needed per watt of energy production can be very low, as well as finding the biomass and so on. And subsurface mineralization, bioethanol, afforestation, peat, enhanced weathering, they all stay down here with costs may be reasonable, but the tonnage is quite low. Geological carbon capture and sequestration tonnage is high, cost is reasonable compared to direct air capture here. Methods are still to be looked at, as we will see in the next slide. Ocean direct injection, of course, tonnage possibility is high, cost is also down here. It's still about finding finance, so this is the way to look at it. If you look at the technology, carbon capture and sequestration, BECCS, soil carbon and biochar, enhanced weathering, afforestation, subsurface mineralization, ocean direct injection, ocean alkalinity, and direct air capture. So there are different methods here. Carbon capture and sequestration tends to be at source at power plants and so on. So the green colors here are in the technology readiness. These are pilot, so yellow is partly achieved and red is untried, undeveloped, or failed. So you can think of it, the theoretical parts, these are not even fully ready, they're partly achieved. This is untried in terms of pilot operates and so on. So for each technology you can look at what is ready, what is being tried, what is being fully operationalized, what is being monitored, whether it's considered secure, and finally whether finance is available. So you can see that most of them are partly achieved or untried, undeveloped, and failed. Okay, so this is what we have to worry about. To look at it other way, in terms of gigaton CO2, various options of storing fossil fuel reserves. There are undiscovered, unconventional reserves which could add the current estimates that exist here in terms of 10,000 gigaton CO2. So the question is whether we exploit it, and what happens if we burn it without carbon capture and sequestration, right? We cannot just burn it just because it's available. But in terms of sequestration, in terms of gigaton CO2, afforestation, what is accomplished and the potential are both kind of small. Same for biomass use. What is possible in soil with biochar, the potential is good, up to almost 4,500 or so gigaton CO2. Wetlands remains largely unknown as well. And here are the times, storage timescales. So you can see that these have decades to multi-decades timescales. So wildfires and perturbations and other things would belch it back out. So you can think of it as getting breathing space to control the warming till we have a better solution. These are in the longer time scale. Deep ocean water and seabed sediments, much longer time scales, but remain kind of unknown. Saline aquifers, high potential, good long-term storage. and depleted hydrocarbon reservoirs, unminable coal seams, basalts unknown, enhanced weathering unknown. So there are some options which have nice long geological type storage years. So these are kind of the range of options and costs and technology readiness and pilot efforts and finances in one basket, so that you can kind of see what is possible and what is scalable. This doesn't give you a complete sense of whether they are really doable. Just because there is a potential for storing in saline aquifers for a long time doesn't mean that it's economically viable, or that it's in a life cycle analysis it's possible right now in terms of transportation, capturing at scale, and so on. Remember that the ideas we talked about, how carbon is only 0.04% of the concentration, so doing large-scale direct air capture or carbon capture and sequestration is still ways to go. But here are the parameters we are working with.